Everyone, so we shall discuss one more problem on the Rankine cycle. In this particular problem, there would be a comparison between the Rankine efficiency and the Carnot efficiency. See, Carnot efficiency is the most idealistic one, ideal form of the thing, and Rankine efficiency is the more realistic one, which is practical in nature, correct? So what would you expect? Which efficiency would be more, a Rankine efficiency or Carnot efficiency? Definitely yes, if the Rankine efficiency would be less and the Carnot efficiency would be more. Okay, we shall try to analyze such kind of problems through this example now. Just I will read out the problem statement if it is not clear. A steam turbine receives steam at 15 bar and 300 degrees Celsius and leaves the turbine at 0.1 bar and 4% moisture. So this is the thing he has given. He has given the boiler pressure, which is 15 bar, even the super temperature, that is 300 degrees Celsius, superheating temperature, and leaves the turbine at 0.1 bar. That means it has the condenser pressure and 4% moisture. What is this 4% moisture? He has given the information regarding what would be the dryness fraction at state 2. Okay, what is that means? X2. What is X2? He has given it. We shall see how to convert in terms of the dryness fraction later. So what we need to determine is Rankine efficiency. Okay, number 2, steam consumption per kilowatt per hour if the efficiency ratio is 0.7. So I guess this is the new factor, efficiency ratio, which is given as 0.7. What is it? We shall discuss while we are solving the problem. Okay. Third one, Carnot cycle efficiency for the same temperature limits. For the same temperature limits which is specified now, we need to find out the Carnot efficiency. Change in the Rankine cycle efficiency and specific fuel consumption if the condenser pressure is reduced to 0.04 bar. So initially it was how much? 0.1 bar. Now what he is doing is he is reducing the condenser pressure to 0.04 bar as indicated here. So this is the normal cycle, 1 to 2, 3 to 4 and 4 to A and B. So 15 bar is your boiler pressure, 0.1 bar is your condenser pressure. So in the later stage of the problem, what he is doing, he is reducing this 0.1 bar to 0.04 bar. So if I reduce to 0.04 bar, how would affect the Rankine efficiency and how would affect the specific fuel consumption? We should calculate once again. Just it is a repetitive problem. If you consider 0.1 bar and do the calculation for Rankine efficiency and specific steel consumption, again you have to consider in the second stage of the problem, you have to consider it as 0.04 bar as your condenser pressure and calculate the same thing again and compare. So it looks lengthy, but it is easy. Okay. Now the first thing, we shall consider the condenser pressure to be 0.1 bar and calculate our Rankine efficiency as similar to the problem just we have discussed in the previous problems. So efficiency is given by net work output divided by heat supplied. Net work output is the turbine work plus the pump work. Turbine work is, you know that it is initial minus final work outputs. So here is your turbine work. So initial is H1, final is H2. So H1 minus H2. So pump work, again initial minus final, here is the pump work, so H3 minus H4. QS is the heat supplied. Where do you supply heat? You supply from the process 4 to 1. For heat set is final minus initial, so it is H1 minus H4. So in order to calculate WT, WP and QS, you need the values of H1, H2, H3 and H4. So we shall just calculate one by one. H1. So for calculating H1, you have to look where my state point is. My state 1 is in the superheated region. If it is in the superheated region, you can take it the value from the directly from the superheated steam tables. So the value is H1 directly calculated value is 3038.9 kilojoules per kg directly from the superheated steam tables. Next, H2. H2, where is my H2? H2 is here. H2 is in the wet region. So if it is in the wet region, how do you calculate? HF plus X into Hg minus HF, which is all taken at state 2. So where is my state 2? Here is state 2. What is the pressure of state 2? 0.1 bar. At 0.1 bar, what is the value of HF? At 0.1 bar, what is the value of HFG? The subtraction of these two is HFG. So you can note it down. Now, what is X2? He has given that the 4% moisture is there. So therefore, if there is a 4% moisture, the X2 value would be 0.96. Okay. it is a mass of, what is the dryness fraction? If you go by the definition, it is mass of steam divided by total mass. In the total mass, how much steam is there? That is the dryness fraction. So X2 is equals to 0.96. If 4% moisture here specified, then you have to take X2 as 0.96. So you know the value of X2, you know the value of HF at state 2, you know the value of HFG at state 2. Substitute it, you will get the value of H2. Now we will go for H3. Look, where is H3? It is in the saturated liquid line. That means if it is in the saturated liquid line, H3 will be equal to HF at that particular state. Where is my state? It is state 3. What is the pressure? 0.1 bar. So at 0.1 bar, what is HF? That is your value of H3. So H3 is equals to this much. H4. So I told you, if you want H4 is in the subcooled region, no doubt, but if you want H4 anytime, you must calculate the pump work. So if the pump work has a different formula again, it has specific volume at state 3 into P3 minus P4. So what is V3? Again, it is in the saturated liquid line. If it is in the saturated liquid line, so it is Vf. Okay, at this particular pressure, 0.1 bar, what is the value of Vf? That will be V3. So you know V3, you know P3 and P4, that is boiler and condenser pressure. Substitute it, you will get the pump work. Pump work is also equal to initial minus final, H3 minus H4, is it? Here it is. So pump work is also equal to H3 minus H4. Substitute it, you know the value of the pump work, you know the value of H3, you can calculate H4 easily from this. So once you have calculated H1, H2, H3 and H4, you can calculate WT, WP and QS. Once you have calculated it, you can calculate the efficiency as 19.3%. This is the efficiency of the Rankine cycle, but the condenser pressure to be 0.1 bar. Now, we have to calculate the second part as the specific fuel consumption. So, first you have to take a note. What is meant by efficiency ratio? So, efficiency ratio is the new term in this particular problem, right? So, efficiency ratio is given by thermal efficiency divided by Rankine efficiency. So, what is the efficiency ratio? Efficiency ratio is given as, take it in a broad letters in your notes, it as thermal efficiency divided by the Rankine efficiency. Efficiency ratio, he has given it as 0.7 here in the problem. He has given it as 0.7 in the problem. So, thermal efficiency required. So, Rankine efficiency you have just calculated it. So, 19.3. Just substitute all the values and calculate the thermal efficiency, which is of about the multiplication of these two. So, it is 13.51. Now, actual per turbine work output. What is turbine work output? This much is the value. See, here is the value of turbine work output. We have calculated it. But actually, how much it would be? Efficiency multiplied with the turbine work output, isn't it? So, when you multiply efficiency with the turbine work output, you will get the actual turbine work output. So, efficiency is this particular thing which you have calculated, 13.51%. Convert into decimal, it would be 0.1351 multiplied by the turbine work output. So, the actual turbine work output is this much. So, this particular value you have to take for the calculation of the specific fuel consumption. You know the formula for the specific fuel consumption, which is 3600 divided by WT, but here it is WT actual because efficiency ratio is given. So, WT actual, you just substitute it, whatever you get the value, that would be the specific steam consumption for the efficiency ratio to be 0.7. So, now how do you find out the Carnot efficiency? So, the Carnot efficiency is always measured in terms of temperature Z, that is 1 minus T minimum by T max. So, what is T max? T1 is your T max. Okay, this is the maximum temperature, which is superheated temperature, which is 300 degrees Celsius, which is given in the problem. That is 573 Kelvin, just conversion factor. Now, how do you calculate T minimum? Where is T minimum? So, either it must be T2 or T3. Both have the same value. If you look into the TS diagram, T3 is equal to T3, T3 is equal to T2, which is the minimum temperature. How do you find out this minimum temperature? So, it is temperature at the pressure of 0.1 bar. So, it is the temperature at a pressure of 0.1 bar. So, T minimum is equals to, look into the steam tables, and at 0.1 bar, you will find the T minimum temperature. Okay, there you can just substitute the values and calculate your Carnot efficiency. Okay, is that clear? So after this, once you have calculated the Carnot efficiency, what is the next thing? Change in the Rankine cycle efficiency and specific fuel consumption if the condenser pressure is dropped to 0.04 bar. I think you can do it very easily. So what you have to do is, whatever calculation you have made, H1 remains the same, but H2 will change to H2 dash and H3 will change to H3 dash. That's it. Okay, even H4 will change because H3 is changing, so H4 will change. So just follow the same procedure and calculate, think the condenser pressure is 0.04 bar, and if you follow the same procedure, once again you will get the same values. Okay, you can get the efficiency for the Rankine cycle as well as the specific steam consumption. Follow the same procedure, just the simple change is that you have to change the condenser pressure from whatever it is given to the 0.04 bar. So the problems looks lengthy, but if you know the methods, it is very easy. Okay. After this, you have to try this particular problem, and you have to submit in the same assignment. If any doubt, please contact me.